Focus of this mini course is random walks on finite graphs and mixing times, but I had also rate of escape in the title, and so I want today to first present in application of the Varopoulos-Carn bound to infinite graphs. Those are interesting in themselves, and also I want to quote David Aldous, who once told me, well, the infinite graph is an excellent warm-up for random walk on the finite graph at the early stages. So when you are in a huge finite graph and you're walking and the time is short compared to the size of the graph, well, the graph seems infinite. So bounds for the infinite graph are often applicable, good bounds for infinite graph are often applicable to this situation, besides being, of course, interesting on their own. Historically, people working on finite graphs came from many different motivations. So random walks on finite graphs and finite Markov chains have so many motivations. I won't enumerate them all, but many come from statistical physics, from computer science, but also from classical probability and infinite graphs. And I want to quote Laurent Solov-Coste, one of the other people who made this trip from starting with infinite graphs, and of course he still continues to work on infinite graphs and manifolds, but he had a huge impact for finite Markov chains. And but he says in his lecture notes that the first time Percy Diaconis asked him a question about finite Markov chains, he was kind of surprised because he was used to making estimates on infinite graphs. He said, in a finite graph, any estimate is true with suitable constants. But of course, the whole game in finite graphs will be for the constants to be fixed for a sequence of graphs, not changing with each graph. Anyway, so let's talk a bit about rate of escape. So let's contrast the two cases. If suppose you have simple random walk in a lattice like ZD, then the expected distance from x0 to xt grows like square root t, or if I look at the expected distance squared, it's going to be to grow linearly. In fact, for simple random walk, the constant is 1, but in general, for any random walk where the increments are bounded or even bounded in L2, we get the distance squared grows linearly. On the other hand, if we take a graph which is corresponds to a free group, so if we take a regular tree, and we do random walk here, what rate does it escape? So the distance at time t grows linearly in t. Can anyone? So the expected distance from x0 to xt. So I don't need to square to get linear growth. The expected distance itself grows linearly. Can anyone tell me what this converges to? For the 3 regular tree in this picture? The expected distance divided by t. So the expected distance grows linearly in time. Linearly with what constant? This is a 3 regular tree. So this is the graph. Every vertex has degree 3. What is the... So this d, I'm sorry, this d is the distance. This is the distance. So how does the distance grow? 1/3, right. So if you look at any point with probability, it's just the same kind of biased walk we discussed before. At any point with probability 2/3, the distance goes up. Probability 1/3, it goes down. So the expected distance will grow by 1/3 every time, except when you're at the root, when the expected distance grows by 1. But it's easy to see, it will only be a finite number of times at the root. So the expected distance is going to be very close to t over 3. So in this case, if I took the distance squared, it would grow. It could grow quadratically, and what I want to say is that suppose if G is a graph, so one can weaken the hypothesis, but let me just talk about the graph with bounded degrees and polynomial growth. I'll explain what that means. Then the expected distance from x0 to xt is going to be smaller than t to the half plus epsilon, for any epsilon. So remember this little o notation, the expected distance is, if you divide it by t to the half plus epsilon, it will go to 0. So what does polynomial growth mean? What is the growth of a graph? So given a graph, we can look at the metric balls in the graph. So the ball of radius r consists of all points you can reach within r steps. And so the growth of the graph is determined by the growth rate of these balls. So of course, in ZD, in the d-dimensional lattice, if I take the ball of radius r, I'm using the graph metric in ZD, which corresponds to the L1 distance. Then this ball will actually, it will be like a diamond, but it's easy to see that the order of magnitude of its size will be r to the d in ZD. So that's an example of polynomial growth. On the other hand, if I'm computing a ball in this, if I look at the ball in this tree example, then the size of the ball is exponential. A ball of radius r has 3 to the order 3 to the r vertices, again up to constant. So you have to sum some geometric series. So that's a big contrast, and it's related to the speed. So you can bound from above the speed of the walk using the growth of the graph. It's not a two-way equivalence, so there are graphs of exponential growth where the random walk still moves at a plodding rate, just like in ZD, and I'll give you some example of that later. But so exponential growth allows for positive speed, but it doesn't enforce it. However, polynomial growth rules out linear speed, and in fact, it forces the walk to behave almost like the walk in ZD, so root t up to maybe some small correction. And we can be more precise about that later. Yes? Can you speak louder? So here I have an infinite graph. I'm not talking now about. And now I'm on an infinite graph. So. What is the structure of the infinite graph? Yes. So you're given an infinite graph. In this, we'll talk later about finite graphs. But right now, I'm talking about an infinite graph that's given to you, and you can compute. And you measure the size of the balls in this graph. The whole graph is given to you. So. Okay. So we'll see this, and again, I will make a simplifying assumption. I will show this to you in the case where the graph is regular, when all the degrees. So all you need is bounded degree, and even that assumption can be relaxed. But I won't prove it to you in the greatest generality. Again, in these sources I mentioned, for instance, in So since Manju was nice enough to mention my books, let me mention one more book, which, so there is a book which I've been working on for the last 19 years with Russ Lyons. So this is and this book is available on the web, and we'll keep it available on the web. Kind of the big news for us is that we just sent it finally to Cambridge University Press. They've been impatiently waiting for the last 10 years. But we finally sent them our final version, except we're still looking for typos, and they are still doing copy editing, but we're finally not adding more material. The last edition was this summer. I wrote a chapter on random walks on groups, which is now in that. So that's chapter 14. And there's also chapter 13 in that book is all about rate of escape of random walks and the connections of that to various other questions on entropy and embeddings. So what I'm covering on this topic here is necessarily, a part of that. But there's also some discussion there of mixing, but that is not the focus of that book. So for that book, the infinite graphs are actually the main focus, and some applications to finite graphs are presented as well. But there's still a chance for any of you who look there and find a mistake, please let us know, and we'll be delighted to add you to the acknowledgments. But many things I'm skipping. So I can assure you that Russ Lyons, my co-author, would never let me get away with proving something in less generality than it holds. So there it's proved in full generality. But here I'm going to take some shortcuts. And in particular, I want to prove such an estimate for the case of polynomial growth, but fixed degree. So it's called the regular graph. And we're going to do that using the Varopoulos-Karn bound. One can do it quite directly from the Varopoulos-Karn bound, but I want to make a small detour into entropy, which is just a very important tool in this subject. So if we have a random variable x, the entropy of x is really something about the distribution of x. So it's the sum over all values x could take, the probability x could take this value times the log of 1 over that probability. So we're talking about discrete random variables here that take finite or countably many values. And so this is the entropy of a random variable. As you see, it's really a function of just the distribution of the variable. Okay, and the key thing about, one thing about entropy is that if x takes n values, then the entropy of x is at most log n. So, of course, log n is achieved for the uniform distribution on n values, and that's because if you look at the difference h of x minus log n, you can write it as the sum of the probability x equals x, or let me abbreviate this as p sub x. So it's the sum of over x of p sub x times and right, so we can write it in this form. So hx minus log n is just, right? I can write it as sum of px times this log because the px add up to 1. And now you just use the inequality that log t is at most t minus 1 to bound this by sum over x px times 1 over n px minus 1, and when you sum these things, you just get 1 minus 1. Okay, so entropy is at most log n. Now, we want to use Varopoulos-Karn to relate the entropy of a random walk to the distance the walk travels. So let's look at, so now consider a Markov chain xt with a symmetric kernel. Okay, so not just reversible, but symmetric. So pi is uniform, is a reversing matrix. So that's the case where I gave you the details of Varopoulos-Karn. And let's look at the entropy of the walk at time t. So we're going to so I have to fix some initial state x0. And then we look at this. So we write it by definition. It's a sum of, well, this summed over all possible y's. And now we want to apply Varopoulos-Karn here. And we're only going to apply it to the second. So this transition probability appears twice. And remember, we're starting at x0. So this is just a transition probability in t steps from x0 to y. So Varopoulos-Karn allows us to bound this below by the sum over y. I'm still writing p of xt equals y, but the second term here, we can bound from, it's in the denominator, so we get a lower bound. That's why this is greater or equal. And then we have the log of 1 over the probability. I guess the bound, I erased already the bound, but the bound, remember, was e to the minus distance squared over xy. So 1 over it is e to the distance squared over 2t. And then we take, right, and then we want to take a log of that. So we get a distance squared of xy, so this over 2t. But there was also a 2 out front, so we get a minus log 2. Okay?
So x naught is x.
X naught is x, that's right. So I should write that, x naught.
Are you still making the assumption that pi x is 1?
Yes. Symmetric means that pi is 1, yes. Yes. So, so these considerations can all be generalized with some extra terms involving pi, but I just want to keep things simple. Okay, so we get this subtraction, and this log 2 can jump out of the sum if we want, because these terms add up to 1. And then look what does this okay, so what does all this mean? This is just the expected distance squared from x0 to xt divided by 2t minus log 2. Okay, so just moving things to the other side, we see that the expected distance squared from x0 to xt is bounded by 2t times the entropy of xt plus log 2. And this already gives you a finer version of this inequality, because remember, Cauchy-Schwarz tells us the expected distance squared is bigger than the square of the expected distance. Any random variable, right? The second moment is bigger than the first moment squared. So the mean square distance, which is bigger than the square of the mean distance, is bounded by 2t times the entropy of the walk at time t plus this constant. And now look, so this can be applied in many settings. For instance, in the case when the graph has polynomial growth, so, and we're doing, so the case I mentioned, random walk on a regular graph. So here I'm stating it for bounded degrees, but I'm only proving it in the case when all the degrees are equal. The general case is very similar. So in the case when all the degrees are equal and you have polynomial growth, the entropy of xt is at most the log of the size of the ball, because xt is a random variable taking values in this ball. But this ball has, right, so the ball around x0 of radius t has volume which is going to be at most constant t to some power, say, let's call it m. If we have polynomial growth, this is the definition of polynomial growth. The size of the ball can be bounded by a constant times a power of the radius of the ball, right? So, so this means that the entropy of xt is at most the log of this quantity. So we get at most the log, well, of ct to the m. So this is just growing logarithmically. This is just, right, essentially m log t. So if you plug that in here, you see that the expected distance squared is order t log t, at most t log t. So it's better than I mean, I wrote here t to the half plus epsilon, but this epsilon is generous. It's really, really you can replace this here by square root of t log t. And if I put a big O here, square root of t log t. Okay? So for graphs of polynomial growth, the walk can escape only slightly faster than in ZD. By the way, it's this bound, so I showed you the proof via Varopoulos-Karn. A similar bound was proved at about the same time with less precise constants, but about the same bound by Kesten in 85, 86. So he also has a paper where he proves such bounds. And he asked whether you really need this extra log term. So is it true that in any graph of polynomial growth, the expected distance grows at most like root t? Or he even asked, what if I restrict to subgraphs of ZD? So I look at ZD and I look at a subgraph of that. But actually, a couple of years later, in '88, Barlow and Perkins gave an example of a subgraph of Z2. So even a recurrent graph Z2, where the expected distance at time t actually grows like root t log t. So although the walk is recurrent, the expected distance can grow a little bit faster than root t, and except for the constants, this type of bound is optimal. So you get some constants from this graph. Actually, another former student of mine, Balint Virag, had another approach to these inequalities, which leads to sharper constants. But in any case, I've just shown to you the root t log t. It turns out to be quite important to understand cases where this log is and is not needed, and assumptions under which you can remove this log term. And I'll come back to this point. What?
One quick clarification. Here you used expectation of distance squared.
Yes.
And then you went to expectation of distance, and you said
Just Cauchy-Schwarz, right? Okay. Positivity of variance. Okay. Any other questions on this? Okay, so this is so this is, if you try to just, I find this is quite remarkable. If you just think of a graph of polynomial growth and just try to prove by hand without this Veropoulos-Karn tool that I just showed you that the expected distance grows at most like t to the half plus epsilon, it's not easy at all. So this is really an example that I think shows the power of this tool. So let's see, when do we finish, Manju? What?
12.
So what?
12.
At noon, okay. So I want to switch gears and talk a little about, so can we get the screen? And talk a little about mixing times. And we will connect to the discussion of escape rates and come back to this. But one, escape rates are an interesting topic in themselves, but they're related to mixing because if I have a large finite graph, I can't hope to mix before I have a chance to reach the whole graph. So the escape rates yield lower bounds on mixing time. And one very interesting point is, when are these lower bounds sharp? When is the obstacle to mixing just distance, and when are there other issues? So all these things I will define. Question? Yes? I can't.
Are there concentration results as well?
So concentration is not going to happen when the distance grows slowly, but when the distance grows linearly, when you have positive speed, you get concentration. Okay, so we need just the light better. And maybe for those, I'm going to do some elementary discussion of mixing. So for those who know that, I'm going to put on the board a question about escape rates. So we said that remember on the 3 regular tree, the rate of escape is 1/3. Consider the following kind of random tree. So since we have Professor Athria here, it's only appropriate to mention branching processes. So look at the branching process where every vertex has one child or two children equally likely. So with probability half one child, with probability half two children. So this will yield a random tree. So here is an example of such a random tree obtained by, so I'm tossing coins as we speak and getting this tree. how fast does the random walk escape on this tree? So, does anyone want to guess? It should be slower than 1/3, right? Because 1/3 on the 3 regular tree, and this is smaller. Yes?
Harmonic mean of one over square root.
So, we have a suggestion of, let's see, 1 over square root 2, that's far too fast, right? So we said it's slower than 1/3, right? Now, so one idea says it's going to be, if you look at this tree, half of the vertices have degree 3 and half have degree 2. So, 1/3, so with probability half, the drift is going to be 0. If you're at this vertex, the drift is 0, equally likely to go up and down. If you're at this vertex, the drift is 1/3. So one suggestion is 1/6. Now another argument says, wait a minute, but we know these vertices have equal probability in the generation of them. But really the question is, what is the frequency the random walk visits these vertices? And we know, at least for finite graphs, that a random walk visits a vertex with probability proportional to its degree. So we should, maybe we should reweight and get 3/5 times 1/3 plus 2/5 times 0, which will give us 1/5. So I'm going to go now into a discussion of mixing. And for those, I will have to start from scratch there. So if you know all that, you can try and solve this riddle. What is the real answer? I gave you an argument for 1/6, an argument for 1/5. I didn't tell you yet which one is right.
So why 3/5 there?
So one rationale for this is to say that we know for random walk on a finite graph, the stationary distribution is just given by the degrees. So this means that random walk on a finite graph, the fraction of time it spends in vertices of different degrees proportional to their degree. So if we have degrees 3 and 2, and initially we create them with equal frequency, then we should reweight according to the degree. So this means the weight would be ratio 3 to 2. Now this argument is suspect because we're taking a fact about finite graphs and applying it to a very infinite graph, and it's not clear that this is legitimate. But that's why I said these are suggestions, and the question is, what is the truth here? Yes? I can't hear. This is an infinite tree. So no. I have one child or 1 or 2 equally likely. There's no P0 is 0, so no leaves. So the tree is growing exponentially. We know, right? We know at level n, this tree will have about 1.5. Right? The mean is 1.5. So at level n, this will have about 1.5 to the n nodes. You can actually obtain some bound for the speed from Veropoulos-Karn. And that's a good exercise, but this bound won't be sharp. But it will give you something. OK, so I promise you to resolve this later, or even better, one of you can tell us what is the answer. OK, so I'm going to switch gears and talk a little about mixing. OK, so this is recalling the notation we've already discussed, the transition kernel, stationary measure, aperiodicity is something that wasn't important until now, but we will be useful when we discuss mixing. Irreducibility of a Markov chain and reversibility, these are all basic concepts that we'll use. So for finite chains, we have convergence. For finite aperiodic irreducible chain, we have convergence to the stationary distribution as time goes to infinity, and we're going to be interested in the rate of convergence. Now, the classical theory considered this problem, and the way the thinking went is we fix a chain. It has whatever 100 states or some fixed number of states. Now we drive t to infinity. I want to understand the asymptotics. And then you easily see this is just determined by the eigenvalues, really by the second eigenvalue. And it's all a kind of an algebraic theory of calculating eigenvalues. Sometimes that's done with orthogonal polynomials. But this theory was kind of old-fashioned and grew out of favor. And it really, the excitement of analyzing Markov chains arose when people understood that there is a better point of view, which is it's not so interesting to take a chain of a fixed number of states, 50 states, 100 states, and drive time to infinity. If I want to look at a long time, I should be willing to look at bigger chains. And so the interesting asymptotics is to say, I want to reach some fixed distance from stationarity, 1/4, 1/10, 1/1,000,000th, but some fixed distance. If my chain is very big, how long would that take to drive the distance to, a 1/4 or a 1/10? So, and this was a point of view that was put forward by Aldous and Diaconis in the 80s, but it also arose kind of independently in computer science as a result of analyzing randomized algorithms. It turns out that powerful randomized algorithms, one famous example is a volume computation by Ravi Kannan and co-authors that relied on running a Markov chain for a long time. And that also, the important thing there was not driving the distance to 0, but really driving the distance below some threshold, but considering very large chains. And the same problem arose in statistical physics in analyzing the dynamics of the Ising model on large finite graphs. So again, mixing and Markov chains have a lot to do with statistical physics. In particular, there are deep connections between a rate of convergence of a dynamics on a statistical physics model like the Ising model and the spatial properties of the model, the spatial mixing properties. It's important in models of evolution. And as I mentioned, it arises in computer science in randomized algorithms. They're also, I put here card shuffling, but you can call it a fancier name. It's measures on the convolutions of measures on the symmetric groups, right? It's the same thing as card shuffling, but there's really a lot of interest from algebraists as well. It turns out that often, both in infinite and finite groups, random walks on the groups give the best insight to understanding the geometry of the group. In fact, I just come from last week. I was in a conference in Geneva, in Lausanne, where there was exactly a combination of people from algebra and probability, all interested in random walks and harmonic functions on groups. Sometimes Markov chains are used in order to sample from a large space. So if I have one simple example is proper colorings of a large graph. Suppose you have a huge graph. You want to color it with a small number of colors. And the proper coloring means that any two neighbors must have different colors. So the chromatic number is the smallest number of colors you need. So suppose there exists a proper coloring, but I want to look at a typical one. How does a typical proper coloring look? Well, how do I obtain a typical proper coloring? If I just have a coloring without the requirement of proper, I can just pick each color independently. But if I want a proper coloring, well, it's tough. How do I get a proper coloring? So essentially, the best method is if we know there is one, we could usually, let's assume we can find one proper coloring, and then we can run a Markov chain which just, you choose a vertex, remove its color, and recolor it with some legal color, something which is different from the colors of its neighbors, and keep going. So each time choose a new vertex and recolor it with a legal color. That's a Markov chain. It's reversible, and its stationary measure is, or the uniform measure on proper colorings is stationary for this. So if it is irreducible, which is something you have to check, then it gives you a method to sample from proper coloring by just running this Markov chain. But then it raises the question, how long do you need to run it before you get reasonably close to the uniform distribution? So that's a case where you have a uniform distribution, but it's very hard to sample directly from. Now, the permutation group is a different example where it's not hard to sample directly from. And there is an efficient algorithm which is not based on running a fixed Markov chain. This is this Knuth algorithm. It actually goes back further, but it became famous after Knuth included it in his book. And you can get random permutation in just by doing n random transpositions, but they don't all have the same distribution. So you take the first card, you replace by you transpose it with a random card, then the second with a random card, and so on. So coloring and easing are examples which are not so easy to sample from directly, and the best method we know are running suitable Markov chains and seeing how well they mix. Okay, so how do we measure distance and stationarity? Since we want to be quantitative, there are different ways to measure, and some of them are good for different purposes. The most important one by far is the total variation, which is just half the L1 distance. So this is the total variation distance between two distributions. We will apply it when one of them is the stationary and the other is the distribution of the Markov chain at time t. And it has several equivalent descriptions. Other one, it's the soup over all subsets of the state space of mu of A minus nu of A, where, again, mu and nu here are two probability measures. It also has an interpretation in terms of coupling. So given two measures mu and nu, a coupling of them is just a pair of variables x, y, so it's a joint distribution on the product space where x has distribution mu and y has distribution nu. But x and y are allowed to be dependent here. Then we always have a lower bound. The probability that x is not equal y is always at least the total variation distance of mu and nu. But if we optimize over couplings, the left-hand side, there always is a coupling which gives this total variation distance. So if you want to see the details of that, either do it as an exercise or, for instance, there's an exposition of these basics in my book with Levin and Wilmer, which there is a link in our in the schedule. Now, total variation distance is decreasing when we apply a Markov chain. So if we have a measure mu and a measure nu, and we move one step forward with the Markov chain, then the total variation distance can only decrease, or it cannot increase. And so we're going to look at this function, the total variation distance, from the distribution at time t to pi. And by what I just told you, this is a monotone, weakly decreasing function of time. So d of t is weakly decreasing in t. D of t is this distance. And the mixing time is just the first time where d of t drops below epsilon. So notice we're also maximizing over the starting state here. So this is called worst case mixing. We're looking at the worst possible starting point. There's also some interest, and we'll come back to that towards the end of this mini course, in somehow starting from a typical vertex, how long does it take to mix? But the basic definition is worst case mixing. And worst case mixing, as I said, there is this parameter epsilon. It turns out that changing epsilon, as long as epsilon is less than half, then T mix of epsilon only varies by a constant when you change epsilon. So we often just fix one epsilon, like a quarter, and call T mix. The mixing time is T mix of a quarter. But if you replace 1/4 by 1/10 here, you will only change it by a constant. Sometimes we care about these constants, but sometimes we don't. Now, one nice property of this variation distance is this submultiplicativity. D of t plus s is at most twice d of t d of s. So, yes? So, okay, and this can be seen in many ways. Let me show you one way which relates to another useful quantity. So d bar of t is defined as the max over x and y. So these are two starting points of the total variation distance between ptx dot and pty dot. So there is no pi here. I'm looking at the total variation distance between starting at x and y. So this is d bar. How is d bar related to d? So on the one hand, d bar of t is bigger than d of t, but it's at most 2d of t. Yes. So d of t is less than d bar of t, which is less than 2d of t. Again, where d bar is the maximum total variation between the distance at time t, of the distance of the distribution at time t when I start at x and y. So, first of all, d of t is bounded by d bar because both of them are just because of convexity of norms, or if you want, just triangle inequality. Because if I take the average of these distributions over when y is averaged according to pi, I will get pi. So d of t is the distance between this distribution and an average of these. So an average is always bounded by the maximum. And conversely, d bar is bounded by 2d of t, because if I want these two distributions, I can just interpolate by putting pi in the middle and use triangle inequality. So I go from ptx dot to pi, and then from pi to dt. So this d bar is an alternative measure of mixing, and d bar satisfies a clean inequality. D bar of t plus s is less than d bar of t d bar of s. The reason for that is d bar of t plus s represents the following. I take two nodes x and y, and I try to d bar of t measures with what probability can I couple the chain starting from x and y. D bar of t is the probability of failure of the best coupling. Now, if I start at x, y, I have some probability d bar of t of failing to couple at time t. If I succeeded to couple at time t, then I can just continue to run the chains for another s steps. So then I will succeed at time t plus s. But even if I failed, I can try again at time in the remaining s steps, and then I have probability of failure of d bar of s. So this is very easy to see from the coupling interpretation of total variation distance. And again, I refer you to these sources to see this done in detail. Now, if you plug in this inequality together with, right, so d of t plus s is bounded by d bar of t plus s, and then this is bounded by that, then you'll easily recover this with a 4, and if you do it a little more carefully, you'll recover it with a 2. So you just, instead of using this inequality, you just repeat the proof. You try to couple from x and pi, you move to t time t, and then try again. So to couple the distribution from x and starting from pi, I first move to time t. If I succeeded, great. If I failed, I can't say that now I'm starting from a point and pi, because the fact that I failed biases the distribution, so then I get a different distribution. So I also have the inequality d of t plus s is bounded by d of t times d bar of s. And that inequality leads to the one on the right. And in particular, we get that if I'm interested at t mix at epsilon, which is 2 to the minus k, I can easily bound it by k times t mix, where t mix was defined with epsilon, which was a quarter. Okay, now, so the transition kernel P always has 1 as the largest eigenvalue, and if lambda star is the largest eigenvalue, which is less than 1, so here I write absolute lambda. Lambda is an eigenvalue of P, and I didn't write there, but I mean, of course, different from 1. Then we have the spectral gap 1 minus lambda star, and the relaxation time, which is the inverse of that. And there's a useful relation between the relaxation time and the mixing time, namely, the mixing time is always at least the relaxation time, well, up to these small corrections. So this is t mix of epsilon. It's at least the relaxation time times a constant that depends on epsilon. And it's at most the relaxation time multiplied. So here there's a log. The epsilon is not important. Think of epsilon as a quarter. But this pi min is important. Mixing time is always bounded by the relaxation time, which is the inverse gap, multiplied by log 1 over pi min. Pi min is the minimum stationary probability. Okay, and this factor, although it seems like logarithmic, it's not too important. Many times our chains have huge state spaces, and this pi min is really small. So this log, it can be very substantial. So often the sophisticated techniques for analyzing mixing times are often all about not paying this price of log 1 over pi min, but understanding when this price needs. So these bounds cannot be improved in general. Sometimes they are sharp, but understanding when they can be improved is really one of the delicate points of the mixing time theory. And it's even of some conceptual interest, the chains where the left inequality is tight have very different nature from the chains where the right inequality is tight. So the left inequality is tight in chains which tend to be mostly either finite dimensional, or mixing of such a chain involves one rare event. I'll give you an example. Suppose I have my chain consists of two big chunks, like two complete graphs, and I have a single edge connecting these two graphs. Okay, so that's a picture. Right, here is one complete graph. I have all the edges here. Here is another complete graph. And I only have one edge connecting the two. So the mixing time here is essentially the same as the time until you will cross this edge. And time, or the mixing time is a deterministic quantity, but it's the time until you're likely to cross this edge. And so if these are two complete graphs of n vertices each, the mixing time will turn out to be order n squared here. And so will the relaxation time. So in this example, the mixing and the relaxation time are of the same order. On the other hand, in examples that tend to be high dimensional, where mixing involves not one rare event happening, but many roughly independent things having to sort themselves out, then the left inequality isn't sharp, and sometimes the right inequality is sharp, but sometimes there's a more delicate inequality where instead of the log, we get a log-log there. And this arises from so-called log-Sobolev inequalities. We won't really go into these, but we'll see some examples of this intermediate behavior later. And I think this is a good time to stop.